The double integrals that we've been working with have been special in a sense that the region R have always been rectangular. So it's all been rectangular regions, and that actually makes our problem easy to deal with. But what we want to do is we want to see what happens if we have now a region that's not rectangular. And you know, those things do come up. If let's see if I can come up with some quick examples of finding volumes. Let's say of a paraboloid, z is equal to x squared plus y squared, and z is equal to 1. The paraboloid and the plane would make up some sort of volume. And if we were to take a look at that volume, the domain or the shadow that this is going to have on the xy plane is going to be a circular shadow, and it's not rectangular anymore. So in that case, we don't have a rectangular region, so we want to approach this a little bit differently. So this is an example of a general region. Another common example is sometimes they have a plane z is equal to 1 minus x minus y or something like that. Let's see if this will work. And if we want to try to see how this thing looks like in the first octant, what we could do is we could try to plot the plane. Plotting the plane is usually not very easy. But one way we can approach this is that we can try to see where it intersects the z-axis, the x-axis, and the y-axis. So how would you find the intersection between the x? How would you find where this plane intersects the z-axis? Not z, but that's something else. What? You set both the x and y equal to 0, and then so you're up on the z-axis, and then whatever z value is, that's where it's going to intersect the z-axis. So in this case, z is equal to 1 is the intersection. What if I want to know where it intersects the x-axis? You set the other two variables equal to 0. And when you do that, you get 1 again. And then similarly, you're going to get this. So what we have is the plane. In the first octant, that plane is going to look like this triangular region. So if we want to look at the volume of this plane, the intersection of this plane and the first octant, we're looking at this shape with 4 sides to it. It's called a tetrahedron. Fancy, huh? All fancy and stuff. A tetrahedron is a 3-dimensional object with 4 sides to it. And here's an example of a tetrahedron. And again, when we're looking for the region R in this particular scenario, the region R is usually the region that's the shadow of this volume on the xy plane. So on the xy plane, the shadow of this volume looks like a triangular region, which is not a rectangular region that we've been dealing with. So we're going to want to be able to find volumes of these things and a bunch of other things where we're going to be integrating a double integral that's not over a rectangular region, but a more general region, whether it be triangular, circular, or any other shape that we can come up with, we should be able to do that. Okay? So that's our task for today. Right? Moises is thinking ahead. We'll get his ideas when we get to this problem a little bit later on. Let's talk about this in general. We have a cool function over here. It's not cool anymore. And instead of a square rectangular region, we have now some general region, which we'll have to refine a little bit more what it means, general region, and what kinds of things we need to do with this. So for now, I'm going to put like a blob shape down here. But anyway, so it gets projected up to the surface again, and then we get some sort of volume that we're looking for. And so that's the general idea. But our focus isn't necessarily going to be on this three-dimensional picture. What we want to do is look at what happens in 2D. And for this, I'm going to simplify my region even more a little bit so that we can work with this. Let's say this is R that we're dealing with on the XY plane. And we want to integrate over this. So there's a couple of approaches, and some regions will allow you to do two approaches, and some regions you might just be restricted to one approach if you want to do it efficiently. So the idea is, you know how we slice bread? We had a square region and we sliced the bread. Well, it's the same idea here. We can think about slicing the bread, except the base isn't necessarily going to be a circle or a rectangle anymore. So if we had the shape that's of anything else, then we could possibly adjust this so that we can slice it a certain way. Now, how you slice it is going to depend on the region. So if we slice it, say, along the y-axis, we're going to get a bunch of slices that might look like this. So that looks like it works out okay. Now, I forget, if we sliced it along the y-axis, you remember the rectangular region problems? If we sliced it along the y-axis, what are we integrating with respect to first? X or y? X, let's see. Yeah, we did the delta x business, right? Where's the sliced bread iterated? Oh, I don't have the notes up yet. It's so funny.
Because you're like, oh, let me go check my notes. Like, you haven't even.
You think that's funny? All right, I do have the notes. It's just not up yet. Well, nobody told me about it, so sometimes I just forget. All right, here's the example that we were doing where we cut along the y-axis first. We call it y star and y devil star, whatever that was. And then so our first integral was with respect to x. Right? That's what you guys said, right? So we're going to integrate this with respect to x first. And we're kind of going to be holding y constant first, right? So now the question is, if this is going to be integrated with respect to x first, what are our limits supposed to be? Oh, I don't have anything here, right? Well, I can't have anything because it's not a square anymore. So what would you imagine your limits of this to be? Let's say, you know how last time we kind of fixed the y value? We'll call it like y star or something. So we're integrating this piece. What can you imagine the x limits to be? It's a more complicated question than what it is. So it's what? The path of the curve. So not necessarily the path, but the curve itself. Right? It's the curve itself. And so I think what needs to be done is you have to take a look at this whole path, which is some enclosed path, and maybe cut this up to two different curves. So one curve would be this, and then another curve, let's see if I can make this look different, dotted, would be this. So this first curve, maybe we'll call this first curve, it's a curve of x and y. It's a relationship between x and y. So maybe I'll call this, should I call this y as a function of x or x as a function of y? X is a function of y. Now, why did you say x is a function of y instead of y is a function of x? You're 1, that's good. So 1, because you're trying to find an x limit, x value limit. That's actually a really good one, a good reason. There's another reason I was thinking about. Just by looking at the graph and looking at what you know about functions in Calc 1 or maybe even in pre-calculus. Yeah, so y is equal to a function of x. The vertical line test has to hold. And here in this example, clearly it doesn't. So there's some issue with that as well. So there's a couple of reasons why. That's the one I was thinking about, but Moises' reason is even better. And that's how I'm going to want you to think. When you're thinking about integrating with respect to x, I want you to be able to look for something with an x in it. X equals something. Okay. So this is one graph, and I could probably assume that the other graph is some other x is a function of another function. Let's call it g2 of y. So now, in this particular y star cut that I have, I'm looking, you have to tilt your head to the right, top to bottom, or if you can think about it from left to right. I said top to bottom, I said bottom to top. But the upper limit minus the bottom limit is what you're looking for. Okay. So what we're saying is that if we're going to integrate with respect to x first, we're going to integrate with respect to x first. Your x value is going to go for some arbitrary y, some fixed y value. Your x value is going to go from a lower limit of g sub 1, and it's going to go to an upper limit of g sub 2. So really, the things that go into this block over here are going to be these functions. So the g sub 1 is the lower limit, and they're functions of y. And then the g sub 2 goes in the upper limit. Now that looks really strange, right? I got limits of my integral that have variables in it, but we've kind of seen that before, and it's really okay with this one, because what are we doing? We're holding y fixed, we're integrating with respect to x, and so after we put all of this information and then put the limits in, all the x's are still going to be gone, because that's our condition for our dummy variable, right? Doesn't matter what the variable is. After you do a definite integral, that dummy variable will disappear. And as long as there's no x's in these functions, which there shouldn't be because we took x out, x is equal to something with a y in it, then all the x's will disappear after you do this one integral. And you may, maybe not, but chances are you're going to have a y left in it. So that's our inner integral in your iterated integral. We have an inner integral now with a y. Now we want, once we get the inner integral here, we're going to want to integrate for all these different y values. So now the question is, what is this outer integral going to be? The outer integral is going to be with respect to y, right? Because this thing in here could possibly be some function of y with the y's in it. I know that all the x's are gone inside of this green parentheses. It's all gone. So now I have something with a y in it. So now I have a y. What should the y limits be? The bottom to the top. The bottom function to the top function, or the bottom number to the top number? The bottom number, we'll call this y1. No, y sounds too much like a variable. Let's just call it a and b. No, let's call it c and d. F and e. We can't call it e because e is a number. F is a function. That's why people start going into Greek letters and stuff, and alpha and beta. So C and D. Oh, let me put it here first before I put it in the integral. So y goes from C to D. So now I have this set up. I can take that to my integral and say this is going to go from C to D. Now this brings me to a very, very important statement that we will make over and over again. I'm dressing it all up to make it seem really, really important. And I'm making it look so important that I really don't want you to make this mistake when you're taking the test or the quiz. So here's the sentence. Outer limits are always constant. So these outer limits that we've established over here, the C and the D, whatever you do when you're doing double integrals and you're finding the limits of integration and stuff like that, which is going to be one of your biggest tasks, the outer limits are always going to be constants. Now the inner limits might be constant, sure, that's fine, but the outer limits have to be constant. Okay? Will you remember this?
Hopefully.
Will you make this mistake on the test? Where's the negative 1 come from?
Your final grade.
Wow. Okay, outer limits are always constant. All right, so now, depending on the shape of a particular problem, a particular graph, we could possibly be looking at integrating with respect to x first or with respect to y first. Doesn't kind of depend. It'll depend on what your situation is. There's some cases where we can do both, and some cases where we're kind of stuck with one unless we give ourselves more work to do. But let's take this first example over here, or one of our examples. Let's do the circle later, or maybe another time, or maybe never. But let's do this one with a plane. Oops. Uh-oh, what happened? There it goes. So let's take our function z is equal to 1 minus x minus y. And let's look at this in the first octant. And let's find the volume of this tetrahedron. Find the volume of this tetrahedron. And remember that our focus is on the xy plane looking at the region, right? So I know that my f of xy is just going to be 1 minus x minus y. So that's just going to be the function. Maybe we can write that down. F of xy is equal to 1 minus x minus y. But then I'm more focused about what's going to happen in the region. Now, based on this drawing, I can see my region. But let's say you weren't three-dimensionally inclined. Are you guys three-dimensionally inclined?
Maybe.
For those who are not three-dimensionally inclined, how would we imagine how to find this on the xy plane? So the key is we want the intersection of this plane, z is equal to x minus y, 1 minus x minus y. We want to see where that intersects on the xy plane. So where does z equals 1 minus x minus y intersect the xy plane? So earlier I asked you where it's going to hit the z-axis or x-axis or y-axis. This time I'm asking you something a little bit different. Same ideas though. Where does this intersect the xy plane? What do you do? Set z equal to 0. You got 1 minus x minus y equal to 0, or x minus y, or whatever. Y is equal to any way you write it. So this is going to be a line that crosses 1, 0, and 0, 1. And so if this is in the first octant, you could imagine that the region that we are looking for is going to be this thing. Okay? So at this point, we still have a choice. And I think for this particular problem, you can do it either with respect to x or with respect to y, and it'll work out fine. So question is, for you, what do you guys want to do? You want to integrate with respect to x first or with respect to y first? It Doesn't matter. So let's integrate with respect to x first. So whenever we do this integral, whenever I do this integral, I like to write out my limits for my x and my y. And since I'm deciding that we're going to, Mimi decided that she wants to integrate with respect to x first, I'm going to put x first and then y second. And I know that my y limits are going to be constant because that's the outer integral. So the x limits may or may not be constant. So let's see what happens to the x limits. So if we're going to integrate with respect to x first, here's what I want you to do. So integrate with respect to x first. I want you to, on the region, draw a line parallel to the x-axis. Through the region. This is, can you guys read? Yeah. Through the region. Okay? So we need to focus on something here. When you draw that line parallel to the x-axis through the region, what you're going to want to do is you're going to draw it from less to greater. So if it's along the x, it's from left to right. If it's along the y, it's going from down to up. And what I need you to do is I need you to identify what function are you piercing to get into the region. And this is an x function, so x is equal to something. So x is equal to some function that goes into the region. And so I look like I am piercing this line over here. What's that line? X equals 0. So in this particular example, x is equal to 0. This line is x equals 0. So that's going to be my lower limit for x. Okay so far? Now, you're in the region, and then at some point, you're going to have to get out of the region. So now you need to identify another function, and since we're integrating with respect to x first, you need to identify x is equal to some function that gets you out of the region. And what is this function that gets you out of the region? So this is x. I see x plus y is equal to 1, right? But I want that in terms of x, or not in terms of x, but x in terms of something. So I'll solve for x, and x is equal to what? 1 minus y. So you need to identify the functions. You need to know these functions. And if you need to solve for one variable over the other, then that's what you need to do. So in this case, we solve for 1. We solve for x and get y on the other side. We have x is equal to 1 minus y. And that is going to be your upper limit. So it goes from the inner limit, or the first limit that you get into the function with, and then it goes to the outer limit when you get to the upper limit when you get out of the function. All right? So what's the y limits going to be? Going to be constants for damn sure. From what to what? 0 to 1. So all you have to do now is to figure out what constants are bounding this whole two-dimensional region in the y. So in the y, you start off at 0, and then you end up at 1. And so that's where you stop. And that's 0 to 1 will be your upper limits. Okay? That's it. So the only thing left to do is set up the integral and then put it into some computer or calculator to solve it. So our integral is the inner integral. We're integrating the function z, or f of xy is equal to 1 minus x minus y. We're first integrating with respect to x. And our x limits are going to be from 0 to 1 minus y. And then we're going to integrate with respect to the other function, the other variable y, limits from constant 0 to constant 1. Okay? So let's see how this thing works out. We should get a number here, right? This is a volume of an actual tetrahedron that we're looking at. So we should get an actual number here. So let's see us actually get a number. This is an easy integral, I hope. Right? So with respect to x, the antiderivative of 1 with respect to x, I think it's x. Next one is 1/2 x squared. And then y is a constant, so that's just y times x. And we're going to integrate this from 0 to 1 minus y. What are we integrating with respect to? X. X is equal to 0 to 1 minus y. This is where it gets a little confusing, so this is why I like to use this notation. I'm saying x is going to get replaced. So I'm going to put 0 in here is going to make everything disappear, so I'm not even going to think about that. So I'm going to put 1 minus y minus 1/2 1 minus y quantity squared minus y times 1 minus y. Boy, even this is tedious. All right, let's do it. All right, let's simplify this a little bit. 1 minus y minus 1/2 is middle, squared, positive, negative. Y, correct me if I'm wrong. There's going to be a good chance that I'm going to be wrong somewhere. I don't know. Confirmed? Have we got the same thing? Thumbs up, thumbs down? What did I do wrong? I think the constant's right. Yeah. So that would make this a positive 1/2. Look okay now? Got Chris's approval. Is that good enough? Move on? Yeah, Nora says yeah. Let's go. All right, so now I have another function, now with respect to y, that goes inside of this brackets, And outside of that, I am integrating with respect to y from 0 to 1. And now it's all with respect to y, and it's a function of y, and so it looks like it's just going to be constant after I work everything out. So let's see. We got 1/2 y minus 1/2 y squared minus 1/6 y cubed from 0 to 1. So adding up a bunch of these things. Oh, this is a plus. Plus. So positive 1/6 is, I think, what I got. Okay, is that good? Boy, I don't want to do that again. I mean, compute integrals. All right, any questions? Okay, so we got a small volume for this tetrahedron. Hope that's right. Well, let's try another problem that the book or the website might have. Let's try number 7. Let's evaluate this double integral from, well, they give us the domain. Now they call it D. Did they used to call it R? I switched my notation. So you can. Oh, maybe they used R because it's a rectangle. That's right. All right. Yeah, we're flexible, right? All right. So let's say our first focus is to look at the two-dimensional region that we're going to integrate over so that we can set up our limits, because we know the function already. The function's just sitting here waiting for us. So let's look at our limits of integration. It looks like I have x goes from 0 to 1 and y goes from 0 to x squared. All right, let me just look at it this way. X is equal to 0. X is equal to 0. X is equal to 1. Y is equal to 0. Y is equal to x squared. Do you see where the region is? There's like 1, 2, 3, 4, 5, 6 different possibilities. Well, everything except for the one that's really the answer. So this is our region. So I think that's in Calc 2 when you had the region, you have to identify the region rotated about some axis. So one of the keys here is trying to figure out where your region is. And in this case, our region is here. All right, so there's a couple ways to approach this, right? Let me see if we could do it the wrong way first. I need to think ahead. All right, let's say we wanted to integrate this with respect to x first. So I want to integrate this with respect to x first. Remember the key? Draw a line parallel to that axis that you're integrating to. So x line parallel to the x-axis. Figure out when you get into the region and when you get out of that region. So I get into the region at what function? Y is equal to x squared, right? But I have an x here. X is equal to something, so I want this in terms of x. So what should that be? So I want x is equal to the square root of y, right? So that's my first function. I'm inside of the region, and then I get out of the region when x is equal to what? I get out of that region when x is equal to 1. The outer limits? Outer limits? 0 to however high this thing goes, and it looks like these two graphs intersect at 1, so 0 to 1. Questions? Yeah. Not according to this. X, if I draw a line parallel to my x-axis, I look at when I get into the region. So I get into the region when x is equal to the square root of y. And then I get out of my region when x is equal to 1. So that's my x limits. But my y have to be constants, and so I have to just figure out where my y starts and where it ends. So y starts here and ends here. Any other questions? Saw a couple of puzzled faces. Is that cool? Yeah. Well, we're doing it the way where after we set up the integral, we're going to get stuck. Yeah. Yeah. Write it down. No, we're going through the process of setting it up, and that's important. And sometimes when you set it up, you might get stuck somewhere. And so you have to know that too. You know, in a test situation, if you set it up and you get stuck, then you have to know when to go back or versus when to continue. Right? You have to know when to hold them, know when to fold them. Yeah. Yeah, so if you don't know that you've done something wrong and you just keep going and you're going in the wrong path and you just keep going, then nobody's going to tell you during the test to say, hey, stop, go back, turn around. You're on your own. So you have to know when to hold them. Know when to fold them. Know when to walk away. Know when to run. You there, sitting at the table. Time to come. With respect to x, so we got our limits, the square root of y to 1, and with respect to y, constants 0 to 1. Okay? All right. So if all I ask you is to set up the integral, which is, I'll be asking you that quite a bit in a lot of these problems. If all I asked you was to set up the integral, then we're done. Okay? But if you're doing a homework or I asked you to continue on and finish this integral, let's take our next step. What's our next step? Well, our next step is to integrate this, right? Let's integrate this with respect to x. X to the 5th plus 1 in the bottom. What? Do we see an issue? So if I clean everything out and I think to myself, this is my thought, back in Calc 2, do I remember any formulas that have this in it? No. No. No formulas. So if there was some reason that I would be expecting you to do a calculation in an integral, and you get stuck with something like this, you have to think, oh, maybe this is not the way to do it. So this is when you stop, stop, stop. Stop, stop. And then, where are we going to pick up from? We're going to stop. We're going to go back and redo this thing. Where are we going to redo this thing from? From when we started to set up our integral, right? We set up our integral. We said, oh, let's do this with respect to x first. Okay. And then now you went through, and that didn't work. So this is where you stop, and this is where you pick up from with respect to y. Now, I kind of butchered this picture already, so maybe I need to redraw that picture again. So let's redraw that picture again. So this time, I'm going to integrate with respect to y first, and then with respect to x. So if we integrate with respect to y, draw a line parallel to the y-axis, and going from less to greater, we're going to enter the function somewhere. And we're going to enter some function, y is equal to something, to get into the region. What is that first function we're going to enter? Y is equal to 0. And then you're going to be inside of the function, and at some point you're going to get out of that function. You're going to get out of that function, or out of that region, via the function y is equal to something again. Y is equal to what? Now it's x squared. Okay? So, what are the x limits? They're constants. That's for damn sure. 0 to 1. So let's set up our integral and see if we have better success with this second integral. So with respect to y first, or y goes from 0 to x squared. With respect to x, our x goes from 0 to 1. You think, wow, switching the order of integration, is that really going to help us? Is that really going to help us? Maybe. Let's see. All right, we're integrating with respect to x. Or, no, sorry, we're integrating with respect to y. So x is constant. The whole denominator has no y's in it, so I can just move that out and leave it out for a little while, and just 6y. What's the antiderivative of 6y? 3y squared, right? So 3y squared, the whole denominator didn't change. We integrated this with respect to y, and so we need to put the limits from 0 to x squared in there. So let's put in the limits. I think if I put 0 in, this whole thing's going to disappear. So if I put x squared in, I'm going to get 3x to the 4th over 4x to the 5th plus 1. Now, is there any promise that I can actually do this integral? How would you do this integral? U sub So whenever you're integrating and it looks more complicated than what it might seem, first thing you should think about is U substitution, right? And then you start thinking about integration by parts, trig substitution, and all those other stuff. But the first thing, U substitution. And if you let U equal to the whole thing in the denominator, there you go. Your x to the fourth is right there waiting to be canceled. Or however you do your integral. Can you just tell me what the answer is? I suppose I do it. Okay. Do I want to change the limits too? See, it's all complicated now. Not complicated, just tedious. 0 to 20? If I change the limits to U? Oh, do you guys do that? No? You just 0 to 1 would be easier. So we'll keep it as an x limit going from 0 to 1. And then now the U substitution, the 20x, 20 into 3. So is that 3 over 20 or something? I don't know. Is this right? Yeah. So ln so ln of 5, ln of 1 is 0. It's ln 5, yeah. All right. I guess this time we can actually check. That's taking long. Okay. So the first method that we used when we integrated with respect to x first was not all that completely wrong, right? The only thing that was wrong with it was that after we do it that way, then we tried to integrate and we couldn't do it. So we switched it around and then we were able to do it. Now there's going to be some problems where you just won't be able to do it, period, because we don't have the antiderivatives of every single function. So that's always going to be an issue for us. So we might still run into something, even if we do it as correctly as we can, we still might run into something where we just can't integrate it. And that's going to be okay. And I don't know if I don't think I'll be giving you a problem like that. For me, I'm more interested in you being able to set it up, and you being able to set it up both with respect to x first or with respect to y first. And that's going to be one of your test questions in your exam. Yeah? Say it again? I think everything that you learned in Calc 2 is about all the possible integrals that you can do. Anything beyond that will require special functions or will require series. And if you get into differential equations, you'll see one of the topics there is series solutions to differential equations, because a lot of times you can't find these functions as functions, and so they define these functions as series. I'm going off on a tangent now here. Thanks, Diana. One of the most famous, not the most famous, but one of the famous functions is the Bessel function. And the Bessel function, where is it? No, I had clicked on the guy. It's a solution to this differential equation, but it's really defined as a series. And there's no other way to define the Bessel function aside from writing it as a series. So it's actually an infinite polynomial, infinite series. And so that's an example of something that you wouldn't have been able to integrate using Calc 2 methods. And so anything that you can't integrate using Calc 2, you refer to it as a series. All right, back to reality. All right, let's see if we can find another type of problem that you might run into in your homework. Let's try number 17, and I guess I'm going to be more interested in setting it up than actually going through the whole computation, so won't be able to check it. Plus, we only have 4 minutes, so we'll see what we can do. So we have a plane. In terms of setting up your integral, the plane is really inconsequential, aside from the fact that you need to solve for z, because you need to write this as a function of f of x and y. But that's not what I'm worried about. I'm more worried about the region. So let's see if we can get the region going here and then set up the integral. So we have x plus y is equal to 1. I think we just saw that earlier, right? It's just a line that goes down like that. And then we have y is equal to x squared. What? No. Y is equal to 1 minus x squared. So 1 minus x squared goes up 1 minus x squared down. So that's our other function. So these are two functions that we're dealing with, and I think that we have a pretty clear cut of what the region should look like. So this is your region. So it looks like at this point we still have a choice. There's going to be some problems, and I don't have time to do one, but there's going to be some problems where you're not going to have a choice what you integrate with respect to. So maybe I'll just make up a region in a couple of minutes. But let's see. This one we can do either with respect to x or with respect to y first. So you choose, x or y. Let's do it with respect to x first, and then with respect to y. With respect to x, a line parallel to the x-axis, and figure out where you get into the region. Some x value, I hope. X is equal to something when you get into the region. So what is your lower limit here? What's this function when you get into the region? So it's this line, 1 minus y. That's your first function. And then you're going to be in the region at some point. You're going to get out of that region with this function. And again, you want an x equals to something. X equals what? So we got a square root going over here, so maybe this is not the best thing to do, but we'll get it set up anyways. So that's your upper and lower limits for your x. And how about your y? Zero to 1. You didn't say constants. So 0 to 1, and then that's it. So you set up your integral. You got your function, solve for z. 2 minus x plus 2y. With respect to x first is what we decided, from 1 minus y to square root of 1 minus y, and then with respect to y from 0 to 1. And this particular problem, we have a choice. We can do this with respect to x or with respect to y. But I won't do that. Because really quickly, can I go to the next page? You guys still copying stuff? Okay. So really quickly, what if your region looked like this? What if we did this with respect to y first? What are your limits? So y is equal to x squared. That's your inner limit. That's your lower limit for the integral, and y equals to 1, and then x goes from -1 to 1. Now, what if you integrated with respect to x first? So if you integrate with respect to x first, it'll be a little bit more tricky. I mean, I think you could still do it here, but you have to figure out what you're going into and where you're getting out of. So this is y is equal to x squared, but if you integrate with respect to x first, you need to get x by itself. So when you get x by itself, then this is a plus or minus the square root of y, so you have to decide is this a positive or negative one. So in this case, it's a negative. So negative root y, positive root y, and then your limits are still going to be constants for the outside. I guess this wasn't impossible. I was trying to think of one that's impossible to do. I guess you'll have to run into one. Good luck. All right, so this is the idea. Just draw your two-dimensional region. Draw a line parallel to whatever you're integrating with respect to first, and then figure out your function limits, and then your outer limits are always constants. Okay? If you learned anything from today, outer limits are always constants.
So I'm going to write that down in the class about constant.
Write it down in your Facebook post. What's your status? Outer limits are always constant.